Welcome everybody. Today's video we are proving the famous Euler identity for complex numbers, which is this relation here. I take a real number phi, multiply it by I so that I obtain a purely imaginary number, and then plug it into the complex exponential functions, which has to be defined yet. And then I end up with cosine of this real number plus I times the sine of this real number. So, and in order to prove this, we need a bunch of prerequisites. We're just stating facts here without proof. First of all, we are going to need the Taylor series or the Taylor expansion of the real sine and cosine function, which means that the sine or the cosine can be expressed for any real number x as a power series. Here in the case of the sine we have these guys here, -1 to the n, and here the odd numbers 2n plus 1 factorial times x to the power of this odd number 2n plus 1. If I take the first term, n equals 0, then I have 1 factorial, which is 1, minus 1 to the 0 is 1, so I have 1 as a coefficient, and x to the 1, meaning x. Then for n equals 1, I have 3 factorial, which is 6, minus 1 to the 1, which is minus 1, and x to the 3, and so on. And for the cosine, almost the same formula, except that I have the even numbers here. So if I start with a 0, I have a 0. 0 factorial is defined as 1. Again, minus 1 to the 0th power is 1, and x to the 0 also is 1, so I start with 1. Then for n equals 1, we have 2 factorial, which is 2, minus 1 to the power of 1 is minus 1, and x squared, and so on. I'm showing you all this for the cosine function. The same applies to the sine function. So here in red we have the graph of the cosine function, the ordinary cosine curve. Now the first Taylor polynomial is when I stop the Taylor expansion after the first term, which is simply 1. Then of course globally this is useless, this is not a good approximation, but locally here at the point 0, 1, this is exactly the tangent line. So the linear approximation, the approximation of first order, which fits the function best locally, or it's the best linear approximation to the function. So here we have the next order Taylor approximation. I add the term minus x squared over 2, and then already between, let's say, minus pi over 4 and pi over 4, this is a pretty good approximation of the cosine curve. Now another term, x to the 4th power over 24. So even here up to the first zeros of the cosine function, minus pi over 2 and pi over 2, this is a very neat approximation. And even better, t3 of x, well, here it fits perfectly up till, let's say, 3/4 of pi, minus and plus. And the more terms I add, the better this approximation gets. And in the limit, if I consider the whole series, I actually get the cosine function. This is the magic of the Taylor series or of the power series approach to real functions. Okay, next we have to talk about convergence in the complex numbers. Now if you have never heard of sequences and limits and stuff like that before, then this is going to be hard to digest. I would suggest you skip forward a bit, because even without this, you can understand the main ideas of the proof, even if it's not going to be as rigorous as it should be. Here I'm really trying to be as rigorous as possible for the viewers who know about convergence. If you know the notion of convergence in the real numbers, then it can be extended to the complex numbers without any problems, because in the complex numbers we also have an absolute value as in the real numbers, and this is the only thing I need to define what a limit is. So I take a sequence of complex numbers and this sequence converges to another complex number, can be written like so: z index z sub n goes to z with this arrow, or the limit of z sub n for n goes to infinity equals z. These notations are both equivalent. If for any arbitrarily small number epsilon, as long as it is positive, I have to find an index n sub epsilon such that for all indices n bigger than n epsilon, the absolute value of the difference between zn and z is smaller than epsilon, or less than epsilon. That means intuitively that if I have a point C in the complex plane, then the sequence of complex numbers, for example this spiral here, converges to this point if after some index all the elements of the sequence are really close to z. This means here the absolute value of the difference between the limit and the sequence elements becomes arbitrarily small. Again, if you hear this for the first time, forget it. This is very hard to understand. You need a lot of time as a beginner to get used to this. And now the most important observation for us is if I take the real part of this sequence, so the real part of every z sub n minus the real part of the limit, then this can be written as the real part of this difference here. This is simply because the real part respects addition and subtraction. And then of course the absolute value of the real part is smaller or equal to the absolute value of this guy here itself, because the real part is in general this length, which is shorter than the whole arrow. And this means this guy here becomes as small as I want to. So by this inequality, I also know that this difference here becomes as small as I want to. And the same for the imaginary part. And this simply means that if a complex sequence converges to a number, then the real parts and the imaginary parts of the sequence also converge, but in the real numbers. And the limit is the real part of the limit of this sequence or the imaginary part of the limit of the complex sequence. This turns out to be very important for our proof. And the most important definition is the complex exponential function, denoted by exp, from the complex numbers into the complex numbers. Any complex number gets mapped to e to the power of z. This e here being the real Euler number, 2.718 and so on, but that's not really important here. As in the real numbers, I can simply define this as a power series with these entries 1 over k factorial times z to the k. And this power series here converges for any complex number z. This is our definition for the complex exponential function. Now what does that mean, that the power series converges, this infinite sum, which is a very dangerous expression? Well, you simply take the partial sums, you sum from starting from 0 up to any number n, and take the same entries. Now this is simply a complex number, and this here is a sequence of complex numbers. And if this sequence converges by this definition here, then we say that this power series here converges. That's also the reason why I denoted the index here by k and not by n as usual, because I need the n here as the index of the associated sequence of partial sums. Whew, okay, that's a lot to digest, especially if you heard it for the first time. So now we can start with the proof of our proposition. Euler found out that, as I said before, if I plug in a purely imaginary number into this complex exponential function, then something amazing happens. This here splits up into a real part being cosine of this number, plus an imaginary part being the sine of this number. And this, of course, is our polar form from the previous video. And the importance of this identity is that I can use it to write the clumsy polar form in a very compact form, which is very, very useful to do calculations with, especially multiplication. But we're gonna talk about that in depth in the next video. Here we're going step by step through the proof. So I use the definition of the complex exponential function and plug in this purely imaginary number phi times I, phi being a real number. Then by definition, this here is defined as this power series or the limit of this power series. And now here, of course, I can write phi I to the power of k as phi to the power of k times I to the power of k. So now we know that this series converges for any complex number, especially for an expression like this. And this means that the real part of the sequence of partial sums converges to the real part of this number, of this limit, and that the imaginary part of the sequence of partial sums converges to the imaginary part of the limit, being this guy here. Okay? Okay, so here I have written down in detail what this means. Again, the sequence of partial sums of this series here converges, and that by our observation B before means that the real part of these partial sums converges in the real numbers, and the limit is the real part of the limit of the complex series denoted by e to the phi I. And the same holds for the imaginary part. So, and now a very important observation. If I take the real part of the nth partial sum, I have the real part of this finite sum, yeah, the same entries as here. And now the real part respects addition, so I can pull the real part into the sum. Yeah, because this is this simple observation here generalized to n, sum with n entries. The real part of z plus w is the real part of z plus the real part of w. And now in this expression here, this is a real number, this is a real number. So the only number that I have to take the real part of is I to the power of k. And the same, of course, holds for the imaginary part. And this means, put together, that this complex number, the limit here of this power series, can be expressed as the limit of this real sequence here, written like that, plus I times the limit of this real sequence here. And now comes a very simple but important observation. For example, here k equals 0, I have 1. The real part of 1 is 1. For k equals 1, I have I. The real part of I is 0, so it vanishes. For k equals 2, I have I squared, which is minus 1, so the real part is minus 1. For k equals 3, I have I to the power of 3, which is minus I. Real part vanishes. So here, all the even exponents give me a real part not equal to 0, and the odd exponents give me a vanishing real part. So I can skip all the odd indices. Same here, except that now the even entries vanish because they give me imaginary part 0, and I have to keep the odd indices. So now this idea with even and odd can be written down formally as follows. For any even index k, I know that k can be written as 2 times m with any natural number m including 0, because I want to start with k equals 0. Then I have I to the k is I to the 2m using potence rules? No, that sounds wrong. Exponential laws, maybe. Exponential laws. This can be written as I squared to the power of m. I squared is -1, so I end up with -1 to the m. So the real part of this guy here is -1 to the m, whereas the imaginary part vanishes because this here is a real number. Now for an odd index k can be written as 2m plus 1, so an even number plus 1, starting with m equals 0 and then taking all the natural numbers. I need the 0 because I want to have k equal 1. So then I to the k is I to the 2m plus 1. Again, using exponential laws, this is I squared to the m times I. This is minus 1 to the m times I. So this here is a purely imaginary number, meaning that its real part vanishes and the imaginary part is exactly -1 to the m. So this here reduces to the first series. I only need to consider the even indices, and in the second series only the odd indices. And now we already know for k even, this here is -1 to the m. So if I express here the even indices as 2m, then I end up with this series from m equals 0 up to infinity over this here, and the same for the odd indices, which I write as 2m plus 1. And now we know this here is -1 to the m, and the same here for this imaginary part. Okay, so we end up with these two power series, and I'll be damned, this here is exactly the Taylor series of the cosine, which unfortunately is just cut off, I think, in my camera frame. This here is exactly the cosine of phi. You have to replace n by m because n we already used. I should have used m here instead, but it's too late. And this here is exactly the Taylor series for the sine of phi. So this concludes our proof. This was a rigorous proof of Euler's famous identity. We only assumed some facts about complex convergence. We actually proved or explained these facts, and we used the fact that sine and cosine can be expressed as a Taylor series, which of course we can prove in this context, and that this series here converges for every complex number, which we also can prove yet. But apart from that, this was a completely rigorous proof of Euler's identity. Okay, to conclude, of course, every video covering this identity must end or must contain this wonderful formula, maybe the most beautiful formula in all of math. So this wonderful little equation connects three very important constants of math. Euler's number, which is mostly connected with exponential growth and differential equations and stuff like that. Pi, of course, you all know where pi comes from, and the imaginary unit I. And the maybe most remarkable fact about this equation is that E is an irrational number, even transcendental, that's even stronger condition than irrational. Pi is irrational, even transcendental, and I is not even real anymore. But if I combine them in this way, I end up with -1, which is, if you see this without knowing the background, almost unbelievable. If you know this formula, then the proof is trivial, because if you use Euler's identity, then you plug in pi for the angle phi, and you end up with cosine pi plus I times the sine of pi. But this here is 0 and this is -1, so that's it. That's almost too easy, but remember, this requires a lot of math and a lot of background information about real functions and convergence in the complex numbers. Okay, if you were able to understand each step, then congratulations. Even if not, I think you may have gotten some idea of how the proof works. And at the very least, even if you didn't understand the proof, you have seen this formula and here this very beautiful consequence. Oh, by the way, corollary means this is a fact that follows easily from a proven theorem or proposition. This is what a corollary is. Okay, thanks for watching. See you next time if you like.